All right, good afternoon, class. Happy Thursday. So I guess for today's class, I'm going to just, well, first of all, I'm going to go over, I did post an assignment, so I'll go over the homework assignment first. Nothing too fancy there, just doing some work involving B trees. And then I'm going to go ahead and just sort of continue with more on binomial heaps. So we'll see how far I get with that today. I'll probably finish that entire topic today, but if not, the next sort of item on the syllabus is going to be graph theory. So I would just introduce graph theory a little bit, and then I'll do some algorithms on graph theory sort of next week and beyond. I'm not going to really have it be very specific, code-wise, but have, pseudocode to understand the concepts of various graph theory traversals and such. But anyway, let's go ahead and just go over the assignments. So let's screen share. Homepage, and then here's our new assignment posted. Oh yeah, so the midterms, I will have them, I'm going to begin grading them. Probably I'm going to try it tonight, but for sure tomorrow or this weekend I'll have them all done. So I apologize for being a little delayed on that, but I guess it's been just a lot of stuff happening at one time. So it's been hard to multi-process everything, but I will have them done. But hopefully the midterm didn't go too bad, so you shouldn't be too stressed about getting your grade back for them. But I'll grade them up this week, and I'll definitely grade them. So we'll have that. I can go over the exam a little bit too, if there was any issues with the exam. So anyway, here's your homework assignment. So basically, we're given this following 2-3 tree. So you have to go ahead and just insert, show the tree after each insertion. So you have to sort of show the steps and then show the final tree after it's done. So a lot of busy work, but nothing too hard, just busy work. But it is due next week, so you have a week to work on this. So shouldn't be any problems getting this together. But you just, given this tree, insert 12th, and after you have 12 inserted using that new tree, insert 4, and so forth. So that's pretty much all there is to do there. So I think insertions are not too problematic with B trees, but deletions can be a bit of a problem. Now for deletion, remember I was in a faculty senate meeting that day, so I posted the video on deletion on my YouTube channel. It's a pre-recorded video on deletion, and the insertion one is in a WebEx sort of session. So that Thursday before that, Tuesday's session is what I had on WebEx like that. So it's kind of a little bit all over the place. And in fact, it ended up being that way already because I was recording on YouTube early in the semester, and WebEx sort of changed, and suddenly it's not allowing me to save to my desktop anymore. So I have to use the cloud-based storage for WebEx. So it already became a little bit inconsistent, but hopefully we're able to sort all that out. But anyway, yes, this case, just do some deletions. So each one has a certain amount of points. I guess the ones that have less points require less work. The ones that require a bit more work are worth more points. So that's, I guess, kind of how I decided that. So given this tree, just show the tree after every deletion. So that's that. And of course, if you're going to use if you're going to actually delete, let's say, so I guess I could have actually had it where we deleted nodes, intermediate nodes as well, but I guess I kind of didn't have, so it's only going to be deleting most, I think, mostly deletes just leaf nodes. So it makes this a little bit simpler. So I guess not too bad. So I don't want to really go overboard with this, but I could have had it where we deleted sort of interior nodes instead, but we'll focus on leaf nodes. It's still going to be relatively challenging enough, I suppose. So it's not going to make the problem that much easier, I guess. So anyway, there's that. And then we have these two questions over here. Just have to answer these two. So I guess here we have a 2-3 tree. We insert elements 1 through n into a 2-3 tree. What's the max and min number of nodes we're going to have in this tree? So remember, for 2-3 tree, we have at least 2 pointers per node, and at most 3 per node. So that's sort of the trick. That's the maximum number of possible nodes. Try to use exact or somewhat exact values. So that one shouldn't be too bad. So it's most at least two per node, 2 pointers, and at most three per node. So it's kind of you can use that way to sort of you actually can use that to sort of compute how many possible nodes you're going to have. So you may have to use some type of a summation formula, like Wolfram Alpha you can use to compute these. So they're very well-known summations you have to use to compute for question 3. Then for question 4, so sort of explain the method. So it can be pseudocode or you can explain it in words. How would you actually output these keys? So given this tree over here, for example, or even first tree, given any tree, how do we actually output the keys in sorted order? So you have to kind of do this sort of an in-order type traversal for a B tree. So describe the steps. They're going to be relatively recursive in a sense. It's going to be a recursive sort of algorithm, if you will. So sort of describe how you would actually implement this approach to output the keys in sorted order. So it's a recursive algorithm, and you don't have to write the actual code, but just sort of, write maybe some pseudocode or like have some idea for what for the actual steps. So basically, just a key is going to be recursive is the idea. So and every single node has the following fields. We have 2 keys, and every node at most. So okay, so it's 2, 3 trees. Okay, so there'll be 2 keys per node at most, and you're going to be at most 3 pointers. You can have at least 1 key per node and at least 2 pointers. So each node is going to be thought of as an array. You have a pointer, then a key value, pointer, key value, pointer. That's how you can sort of visualize each node's structure. You can have to traverse each node. If you see a pointer, you do something. If you see an actual key value, you do something else. I don't know, I think I might have given that away, but it's fine. It's not meant to be really anything super challenging. So anyway, that's our assignment 5, and it's going to be due next Thursday. So I could actually make it due on Friday because that way, if you have any questions during office hours, I'll be available in person on Friday and I'll be available through WebEx. I'll probably make it due on Friday actually. So that way you have the office hours as well. You can ask me for help there as well. But of course, you can ask me tomorrow as well. I'll be in office hours on Friday, but also next Friday as well. If you have any last minute questions on anything regarding this assignment. Yeah, so okay, so I guess it's confirmed. We'll have it due on next Friday. So I'll update the due date after class today. So, I mean, a lot of busy work here, but I guess there's no real trick, just busy work, which I guess it's kind of a bummer in its own way. But at least it's not going to be something where it's just like you have no clue. It's just busy work. So let's go through those videos on B tree insertion deletion as your guide to these problems. So let's go ahead, and I think that concludes the homework assignment. So let's go ahead and go back to our OneNote and sort of continue from last time's content. So basically, I went over priority queues or binary min or max heap last time. And we went over that. We went over how to insert, how to bubble up, bubble down for deletion. Also, we went over build heap operation, which is O of n time to construct. So if you have an array given to you and you want to create a heap out of that array, you can do a build heap operation that does that. So now I'm going over this binomial tree sort of structure. So we have the following few binomial trees right there. So we have a B0 tree, a B1 tree, B2, and B3. And it's very simple. It's a very nice, elegant sort of structure for this. So the 0 tells you how many nodes you're going to have. So B0 means you're going to have 2 to the power 0 number of nodes, or 1. For B1, 2 to the power 1, B2, 2 to the power 2, and so forth. So basically that index number will tell you 2 to the power of that index is going to tell you how many nodes you have in that tree. And the height is going to always be height k. So for a B0 tree has a height of 0, a B1 tree has a height of 1, and then a B3 tree has a height of 3. And also the root for a tree always has a height. So for a B3 tree, the root will have a will have a degree 3. So we see here for B2, the root will be this node right here. This will be our root node. Then it has a degree of 2. These two sort of pointers as a degree 2. For B3 tree, this will be our root. It has a degree 3. And degree really means how many children it has is really its degree, essentially. So it has degree 3. So it has 3 children. So for B4 tree, root would have actually 4 children. Height would be 4. So the simplest way to also imagine this is a very nice recursive structure is that it's just sort of a combination. So for BK tree, it's a combination of two BK minus 1 trees. And one of these two roots will be the root of the entire tree. So because of that, it's a very nice, elegant structure right there. We can very easily compute that a height, so number of nodes in the BK tree is 2 to the power of k. It's very simple to compute. We can do it almost inductively. We can sort of show that because a BK tree is a combination of two BK minus 1 trees. So very simple to actually show that. And the height will be k. And also another property is that if we were to rip out the root of a BK tree, then all the subtrees, we're going to have a B0, B1, B2, and BK minus 1 subtrees you're going to have, basically, which is actually very nifty because it's going to be very useful when we do binomial heaps. So we have to sort of use this binomial tree structure, and we're going to use this structure to create binomial heaps. So that was sort of a recap a bit from last time. Well, not a complete recap, but a little recap on this binomial tree structure. So let's go ahead now and go over some examples. Let's go over a binomial heap. So next sort of note. All right. So basically, a binomial heap, well, I guess it's going to be a priority to queue type structure. Priority, I guess it's not really going to be a queue in a sense, but it's going to be priority queue or priority tree, I guess I'll call it, right? Just because. So same idea. We'll use min heaps for our examples. So obviously what's going to happen is that the root element in the tree will have the smallest element among all the elements in our tree. And for every level, for every node, the parent, or that node, sorry, that node will have a smaller value than all of its children. So just keeping that same sort of heap property. So we're going to have to maintain this property. So we'll use min heap for right now. So then for any node its value is less than all of its children. Put it here in parentheses, since we will use min heap structure. So that reason we'll have this maintained. And of course, then the root of the tree is the smallest element. So once again, same concept like using any binary min heap, same idea with a binomial heap. We're just going to have, it's going to be in different kind of fashion, but same concept. Parent will be smaller than all the children. That's how we're going to maintain this. So the thing is that, so for a binomial tree, the amount of elements is always a power of 2. So we notice that for a B0, it has 1 node, a B1 has 2 nodes, a B3 has 8 nodes. So now, it's not going to always be the case we're going to have a power of 2. We could have 5 nodes in our priority queue. So what we're going to do is we're going to maintain, so going to maintain a forest of binomial heaps. Well, I mean, I guess I'll say binomial trees. Say binomial trees, and each binomial tree is in heap order. So each of these binomial trees are going to be binomial heaps, but we'll just say for now, we have a forest of these binomial trees or slash binomial heaps, basically. And we're going to sort of link these trees together. So yes, so it's interesting. So a forest is a collection of trees. So even in computer science theory, I mean, we have all kinds of weird, notions. We have for a tree, we have a root and leaves, right, which kind of models after actual trees. And I guess a collection of trees is a forest, which I guess that does make sense, not just in CS theory, but like in real life also. A forest has many trees. So it's, I don't know, I always kind of thought that was neat, or that neat, but anyway. Um, so we're going to have, and then also we're going to also use is we're going to, let's see, okay, so no duplicate um, binomial trees allowed in the forest. So we're not going to have more than one B0 tree. We're going to combine those trees together if we have duplicates. So we're going to merge duplicate binomial trees. We're going to merge them together, basically, is the idea. And here's some extra notes. I'm going to get my notebook so I can read this easier. So here's my extra notes we're going to have. We're going to, so I guess the largest binomial tree, largest binomial tree will have the height O of log n. And that's kind of important, I guess, because if let's say, so if you want to update a node that's currently in your binomial tree or heap, you want to bubble it up to the very top, then I guess the good news is this will take no more than log n steps. So it's not going to be worse than using a regular binary sort of heap. And here's like the really important concept. So we're going to represent the size or the amount of nodes in a binary representation, binary number representation. And this actually makes this problem really nifty, actually. So because of this, so then we can determine how many of what type of binomial trees we have in the forest. I'm going to move this down a little bit. So this is actually really great because having this, if we can use this binary number representation, we can actually know how many different trees we have and what kind of trees we have. So it's going to make this whole merging process very simple and kind of mechanical in the way, in a way. That's sort of the idea. So let's go ahead and just sort of draw out some example binomial heaps, and just so we can kind of make sense of what that last bullet actually means. Let's go ahead and draw a couple of examples I have worked out over here. So we're going to have the following. We're going to have sort of one binomial tree in this situation. So we're going to have, let's see, we're going to have 7, 5, 7, 10, 8. Maybe I should have used circles to accomplish this. I guess I'll go ahead and I'll put circles around so it's a bit more faster, I guess. It's not a very straight circle, but I suppose. Okay. So this is going to be actually one B3 tree. It's going to be obviously a mini heap order. This is going to be a B3 tree, binomial tree of 3. So it has a height of 3, 8 nodes, and the root has 3 children. So we can do the following number we can put at the very bottom, just here in blue. So there's 8 nodes in this heap, and that number at the very bottom, I believe, is the binary number representation for number 8. So what these numbers will tell us is the following. This tells us the amount of B0 trees we have, the amount of B1 trees we have, the amount of B2 trees, and the amount of B3 trees we have in the structure. So we can see here we have no B0 trees, no B1 trees, no B2 trees, we have one B3 tree. That's what these numbers tell us. We use these numbers, we have the size of the input represented as a binary number to very easily be able to determine how many trees we have and what type of trees they have, and also it'll be very simple to merge to binomial heaps. Let's go ahead and do another example beside this one. So I'm going to go ahead and have, let's try this one out. Let's say 2, 6, 7. I'll have 5, 8 all by itself. Go ahead and actually circle these. So there'll be nodes in our, like that. So right now, this is not going to be really one binomial tree. It's going to be several binomial trees. I'll use a green pointer as a way to link these together. So I'll use green because I guess we're talking about forests and whatnot. So green and forest does seem to sort of make sense. So we have a collection of binomial trees. Actually, I'm going to modify this to be B3 and green this time to be consistent here. We're going to have a B0 tree, a B1 tree, and a B2 tree in this example. So we can think of it as, if you write this out in binary, we'll have 0, 1, 1, 1, which is, for this instance, it will tell us we're going to have one B0 tree, one B1 tree, one B2 tree, and we're going to have no B3 trees. So we use these, use this a binary representation to help us out. So it's very easy to tell. So you have 7 sort of nodes. This is the only formation you can possibly have. So we have several of these trees, and we simply link them together. And we're going to maintain a pointer that's always going to know which one's the smallest of all of them. So I'm going to put a green pointer on this one, and on this one. So we always know which one's the smallest element. So we have these trees, and the smallest, the root of all of them is going to be the smallest element among all of the elements in our tree. Also, another sort of nice property we can see here is that no matter how big n is, we're going to have no more than log n number of binomial trees. I'll also put this over here as well. Put this below. So in the worst case, we could have one tree of height log of n if you have only one binomial tree for the entire collection. Otherwise, we can have at most log n number of trees. We have 7 elements, so we have 3. So it's not quite exactly log 2 of n perfectly, but it's relatively log of n. Because if we have our size n, then if we want to represent this n in a binary number representation, then we're going to have log n number of bits with respect to the size of the input. So we're going to have at most O of log n binomial tree / heap in the forest. It's also nice. So therefore, if we have to find the min in our structure, we could of course loop through all the roots for each tree. That takes O of log n time. Because the thing is that if, let's say, I don't have the min stored anywhere, I would have to go through each tree and compare it to find the min. But it's only going to be log n number of root nodes, because we're not going to have more than log n number of trees. We have to loop through all these. That will not take O of n time, it will take O of log n time, because there's only going to be log n number of trees. So a few interesting sort of concepts. So the biggest tree will have the height the biggest tree will have a height of log of n, and most will have log n number of trees in our forest. So it's a few interesting sorts of concepts there. So that's sort of how we actually represent and how we can show sort of our binomial heap. Let's go ahead and do an example to construct insert some elements into our binomial heap, and also delete, just so we can kind of see how it all works. And of course, we'll do a lot of analysis on this after we're done. Let's go ahead and do some examples first. I think examples really help us sort of see what's actually going on with this structure. Do some examples, or example, I guess, in this case. Just underline this. That seems more official, underline some example. So, okay, let's first go ahead and sort of have our first representation. So I'm going to use 4 bits. I mean, typically you would add bits in as you insert into our tree, but just to make it simple, I'm going to go ahead and just have our following binomial heap will have 4 bits I'll use, so it's empty. There's no B0, B1, B2, or B3 tree. Okay, so what I'm going to do is I'm going to basically, first I'm going to insert 4 into this tree. So inserting 4 by itself, we're going to insert a B0 tree into our current tree. So we have to insert a B0 tree into our structure. So if we add a 1 to this, our result is going to be, so we're going to have to just add that one sort of 4 sort of element into our tree. So we're going to have 4 all by itself. So that's all we use so far. So it's empty tree, so really nothing really had to be done there. But we're going to constantly, whenever we insert elements into our structure, we're going to always merge a B0 tree into our current forest. Now, right now, we had an empty forest, so we just added this one sort of tree. So now we have the following scenario. The result now is going to be this structure. We have one B0 tree and no other trees in our structure. Okay, let's go ahead and do some more insertions. So I'm going to now insert 5 into my structure. Insert 5 into the structure we have right here defined. So we have this structure right there. Insert 5 into it. Okay, so currently we have this 4 by itself, like that. And we have the following way of representing this. Oops, I don't want to make the shape. That. So what's going to happen is, well, we're going to basically, we're going to, I guess, add a B0 node into our structure. So I'm going to, I use red over here. So we're going to go ahead and we're going to insert this 5 into our structure. So we have our current scenario. We have 0, 0, 0, 1. We're going to add a B0 tree into our structure, which will cause us to have to merge. Right there, at 1 plus 1, we already have a B0 tree. We're going to have to merge this with one of our B0 trees. And then we're going to end up getting a B1 tree, which I would not have there. So we're going to have to merge this this B0 tree we currently have, which is that 4 node. We're going to merge it with the 5, and the smaller one is going to be the root. So we're going to have the following tree. It's going to be our result. And this is going to be essentially 0, 1, 0 is kind of going to be our guide to help us out. So we have one B1 tree, 0 B0 trees, 0 B2 trees, and 0 B3 trees. So we have to basically just merge because we can't have more than one B0 tree in our forest. You have to merge them. And seeing here, we have our binary number representation. We always add 1 to our current formation, so we know exactly which sort of trees we have to merge together to get a correct binomial heap structure. So that's what we have so far. Let's go ahead and just continue. Let's go ahead and insert more into our tree just so we can do more examples. I'll insert 2 next. So actually currently, I'm going to put this here like this. So I'll put the green pointer, which denotes this is my smallest element in my structure. So I apologize for missing that earlier. And we still have this 4 like this. And then 4 is going to be the smallest element in our structure. So we have this one pointer that always points to the root or the smallest element in our structure. So we can very quickly retrieve the smallest item. Of course, we could traverse our heads of all of our trees, but this is faster to maintain a pointer that always points to that smallest element. Okay, so now I'm going to go ahead, I'm just going to copy and paste it instead of redraw this whole thing. And the benefits of using one node over regular classic whiteboard. So I'm going to now insert 2 into my binomial heap. Insert 2. So I'm going to paste this over here. Excellent. Nothing bad happened with that. Here's our current tree. So again, as always, we're going to have to create this new node. We're going to have to merge this B0 tree into our current forest. So we always keep on just taking a B0 tree and merge it into our current tree. So the result is going to be, as always, just add 1. I can draw this tree, would be nice. So we're going to add the following. We're going to take this, we have no B0 trees in our structure, so we're just going to add this here. And now here's going to be our setup. We're going to have a B0 tree and a B1 tree. So in other words, we're just going to kind of connect this B0 to our current forest. So the result of this is going to be the following. We're going to have 4, 5, 2, that, to circle these together. And we're going to connect these trees together. We're going to link them together. So we have two binomial trees, a B0 tree and a B1 tree, and we're going to maintain that this is our smallest element. So it's very simple because we already had our last smallest element, so a new element to be inserted is going to either be smaller or not smaller. So we can just easily just compare it and know that 2 is the smallest element in our structure, and then our schematic looks like this. 0, 1, 1. Which means we have one B0 tree and one B1 tree in this structure. Those last two zeros are kind of, you don't need those, but I just put those there so there's some organization with this structure. But that's going to be our resulting B tree. Let me go ahead and maybe just put some arrows here just to kind of, just like, so we can kind of, for note taking, it's easier to follow. In case you missed class, then this will kind of help. So it's going to be the result after we merge. So now let's go ahead and just do some more insertions. Let's keep practicing this. So I'm going to insert 7 next. Insert 7. I'm going to go ahead and sort of copy this. I'll have to redraw that, which will save me some time. Excellent. That didn't cause any problems. Let's insert 7. Well, as always, we're going to create a B0 tree. Which will be right there. It's a B0 tree right there. We're going to have to merge it into our current binomial heap. So as always, well, we're going to add 1 to our current sort of scenario. And we already have a B0 tree. So we're going to have to merge these together and merge these two together as well. So we're going to have this formation. So we're going to take our existing B0 trees. You also have to maybe have some extra data structures to maintain. We have to also know which sort of trees we have. So of course we can sort of, sort them or have them arranged in a certain way so we know exactly all of the, we have to have all the heads pointed together so we can traverse through all the heads essentially. So we can have these set up where we have them arranged, where we have like the biggest tree and the smallest tree and so forth. We have to sort of know which tree is which, but that wouldn't be too hard to maintain because we would have just sort of the biggest tree on the left, and then we kind of have it in that type of format from left to right, the biggest, the smallest tree in our structure. So we know that this 7 has to merge with our B0 tree, with this tree over there. So we're going to merge these two together to create the following. So we're going to have 4 and 5. I'll just sort of circle these. And we're going to merge the 7 and 2 together to get, oops, we're going to have 2 and 7 as our other tree. So we just merge these two B0 trees together, and it'll end up looking like this. But the problem is, and then 2, of course, is our smallest element, but the problem here is that, well, we don't want to have 2 separate B1 trees. We want to merge those 2 B trees together, which we can just simply do by just merging them. So I'm going to go ahead and just copy this and change a few things. Because right now, that green line, that means that that's sort of we're connecting 2 different trees. So we have a B1 tree over here. That's a B1 tree. Another B1 tree. You want to merge them to make a B0, or sorry, make a B2 tree. My mistake. So what's going to happen now, the result will be this. Rid of this. Not make that green. So green denotes connecting 2 different trees. So we have first this, and we have this. Now we're going to have a single B1 tree. So now we're going to have the following schematic. change the shape state. There we are. So now this is going to be one tree. This entire thing is one tree. Before, we had these two trees, these two B1 trees that were just connected, but now we just combined them, we merged them into a B1 tree. So we had to do two merges because the first B0 tree, we had to merge the two B0s we had, and then we had to take that resulting B1 tree and merge it to our existing B1 tree to create one B2 tree. So we had to do more than one possible merge over here. That's okay though, that's sort of the result of that. So that's going to be our resulting tree right there. So I guess I'll continue with this, but hopefully we're still doing all right. Let's insert some more. So I have left over here, so I'm sure I have. I got plenty. So, okay, so perfect. So I got 7 more examples. So we keep practicing this. So let's go ahead and insert 6 next. I'm going to copy this tree once again, so I'll have to redraw all that. Using this updated tree as our result, I'm going to now insert 6 into our binomial heap. 6, I think, yes, okay. Insert 6 next. Right. I'm going to just paste this right there. So, as always, I guess I'll keep this arrow. So we always want to make sure we know which sort of node is our smallest element in our entire structure. So 2 is the smallest right now. So now I'm going to go ahead and insert 6. So as always, what we're going to do is we're going to create a B0 tree. It's just a sort of a single tree by itself. This one, sorry. And we're going to merge it to our current sort of binomial heap. So this requires no merging because we're going to add 1 and we have no B0 tree. So we're not going to have to do any type of work, just link these two together. So the result now will simply just be, I guess I can probably copy and paste this over here as well, just to save a little time. So get rid of this part. And this 6th node, sort of, I'll move this to right to left. And the result is going to be this tree over here. We're going to have 6 all by itself. And we're going to simply just connect these two together. So we have a B0 tree and a a B2 tree, my mistake. We have a B0 and a B2 tree is the result of this. Which this binary representation of this number right there will tell us that one to the very right means we have a B0 tree, we have no B1 tree, we have a B2 tree, and no B3 tree. So that's our guide, basically. So you always can kind of very easily can always tell how many trees we're going to have, what type of tree we're going to have, and we always can know which trees to merge together. So let me see, how many more do I have to do? I think I'll insert use 2 more possibly. Yeah, I think 2 more is going to, so maybe we'll see. So next I'm going to insert is 10. I guess I want to try to challenge this. Okay, I think 10 is good. 10 is going to be a good insertion. So a few more insertion just to practice this some more. Nice big example. So that way we can kind of see what's going on. Then we'll do some analysis of all of that towards the end. So I'm going to insert 10 next. To just paste this over here. Here's our current binomial sort of heap. It has these 2 trees connected together. You have a B0 and a B2 tree that are connected to each other. So I'm going to go ahead, as always, we're going to have to create a new tree. Upside of a new B0 tree, we're going to have to merge it into our current scenario. So of course, we're going to add 1 to this. So we can see we have to merge 2 B0 trees. So we can definitely see we do have that 1 B0 tree in our our forest, which is going to contain that 6. We're going to merge those two together to create a B1 tree, and then we'll also have a B2 and a B3 is still going to be 0. So what's going to happen is these two, the 6 and the 10, will have to merge into a B1 tree. So the result now is going to be, so we're going to, I'm going to try to fit this all here if I can. We're going to have a 2, 4, 5, 7. A little different shape, I guess. That's kind of running out of space, so a little different shape, but still the same exact tree. Same thing, just I kind of made it sort of narrower, not so wide like the one to the left, because then, well, you know, I'll keep it the same. I'll try and make the same shape. So we'll have, let's say, well, 2. Ended up still kind of being the same. That's, you know what, that's okay. I tried. So we're going to have 6 and 10 like that. Just those two B0 trees combined to make that B1 tree with 6 and 10. And we're simply going to just link, always link these two trees together, and 2 is still the smallest sort of node in our structure. And then this will give us, this will be sort of the schematic we have. So we have a B2 and a B1 tree, just like that. So I'm going to do 2 more insertions to sort of, you know, then it will create one big mega tree at the end. So I'll do 2 more insertions. So I think I'm going to look at my notes here to make sure I in paste. So insert 1 and insert 0. So insert 1, then insert 0, and then we'll be done with insertions. And then we'll go ahead and do some analysis of this. So, okay, I'm going to now, I'm just going to copy this tree and insert 1 next. Let's go ahead and insert 1. I'm going to just paste this. Perfect. So, as always, if you insert 1, we're going to have to just basically create sort of a new B0 node, as always. Just put that there. We're going to have to merge this B0 sort of node into our current binomial heap or our current forest. So again, as always, we add 1 to a current schematic, and we have, so not going to actually do any merging because we don't have a B0 tree to merge with, so we're going to simply just link this to our existing structure. So that's going to be the result. So essentially, let me go ahead and just copy and paste all this out to redraw all of that. Put this over here, this, and actually that. And then the result is going to be just this, but then we're going to move this pointer now because 1's my smallest element from now on in my structure. We have our sort of structure arranged where we have the leftmost tree will be the biggest, and it goes from biggest to smallest like that. So that way we can easily iterate through, so we know exactly which tree is the biggest and smallest. Now, what actually would happen in reality is we have a pointer that points that biggest sort of node, or biggest tree, sorry, and these will all kind of link together. So you can kind of traverse through all of the all of these sort of trees. We'll have one pointer that just only points to that smallest element, so that way we can always access it very quickly. But we'd actually have that structure, but I won't really go over all the details of it just because it'll take too long in this class to do all that. But we actually have a pointer that points to that biggest tree, and that's we can kind of iterate through all the trees in our forest. But anyway, that's how we do that. But I'll just go ahead and just write this out now. So you have 0, 1, 1, 1. That's going to be our schematic here. And now we're going to insert 0 and cause all kinds of mayhem in this situation. Let's go ahead and do a last insertion of 0. Then we'll go ahead and talk about sort of analysis of all of this. So let's go ahead and do that next. So I'll go over here and actually copy this tree. but insert 0 at the very end. Okay, so then I'm going to go ahead and just paste that right there. Perfect. And okay, so insert 0. So as always, what we're going to do is we're going to, they might do this from top to bottom maybe. So I'm going to put this above, put it to the side actually. Have to do several steps in this example. So inserting 0, as always, we're going to have to just basically sort of create a B0 node. We're going to have to merge it into our current sort of binary or binomial heap. So as always, we add 1 for current schematic, and then you have to merge these two B0. We have a B0 tree over there and over there. We have to merge these two together. And the result is we're going to create a B1 tree to be merged with our existing B1 tree. Then we're going to have to merge the result of that into our B2 tree. And then we're going to have that. So we're going to basically have one B3 tree, but we're going to have to go through several amounts of merging to make this work. Let's go ahead and sort of work this out step by step. So the first step is we're going to have to merge a 0 to that 1. So I'm going to copy this. I'll have to redraw all of that. So the first step is we're going to have to merge 0 and 1. And 0 is going to be a smaller element, so 0 is going to be the smallest among everything in our tree. 0 over there, and 1 would fall below. We're going to have two roots basically, and 0 is a smaller, so that's going to be the root of this combined tree. So I'll make this like that. And now we can see here, now we have a problem. We have these two B1 trees here and here. So we have to go ahead and merge those two trees together. So the result now, I'm going to merge those two trees. So I'm going to, again, just copy this so it'll be easier than writing the whole thing out. Sort of modify it a bit. So in this case, what's going to happen, you're going to merge these two trees together. So we're going to have 0 is going to be the root of this tree. Make it look a little nicer. Hold on, I'm going to go ahead and just up a little bit so it looks a bit more sense. It didn't really help a whole lot, but anyway, we merge those two trees together. I'll just maintain this green area there. So we merged those two trees together. So now we have these two B2 trees because we first took our B0 tree, merged it with this tree to make a B1 tree. Then it merges B1 tree with this other B1 tree to create this B2 tree. Then you have to go ahead and combine these two B2 trees to make our B3 tree, which is not going to be anything too fancy, but I'll just copy all this. I'm going to first copy this, then I'll put the arrow there. It's kind of not much busy work there. We're going to just simply merge these two together. Just take these. Now we have our B3 tree. Actually, oops, I made a mistake. Actually, like this. There we go. That's what I'm supposed to do. So now we have our B3 tree now. So we have to basically we have our two head pointers, and then so this case, so over here it was like this. So we have these two B2 trees, and this one has the following root is going to be 2, that one's going to be 0. So the smaller of those two is going to be a root among all of this. So then 0 is going to be the root of this entire structure. That's going to be a child of B0 now. So now we have one big B3 tree. there's our result. We can see here, we have a height of, we have 8 nodes, we have a height of 3, and a root has the actual degree of 3, so it has 3 children in the root. So this is a B3 tree. So having that last insertion causes us to actually have to do a lot of merges in our tree, but that's sort of the case. So now the idea here is that each merge is a constant operation. All we have to do is look at our 2 heads and just pick the smaller of the 2. That's going to be the root of our entire tree combined. But we have to do at most log n number of merges. Let's go ahead and sort of write this whole thing out, and then we'll probably be done after this, but I'll just write some notes out over here. So insertion analysis. I'll put like a line here. Analysis of insertion. So basically, we have to simply create, a B0 tree every time, and then simply end merge with our binomial heap, which is going to be a collection of binomial trees. Remember, binomial heap could contain a lot of binomial trees, and we kind of link them all together. That's how we sort of implement this structure. So every time we have to do a merge, so each merge takes constant time. Because really, all we have to do is compare. So we know basically where the, because since we have our binomial heap arranged, we have the biggest tree to the left, and then we have our smaller trees side by side, we kind of can really quickly can tell where our, well, we can have more pointers for this, but really merging 2 trees together is pretty fast. It's O of 1 time to merge 2 trees, or to merge a B0 tree. Now, the thing is, in the worst case, however, we have to merge each binomial tree in the forest to bind to a BK tree. Okay, so the beauty of this is that we're going to have at most log of n number of binomial trees. So all of this will take O of log n time to actually compute. So worst case, insertion takes O of log n time. Because each merge is going to be constant, but in the worst possible case, we have to go ahead and merge with all of our trees in our forest. It's going to be at most log n number of trees. Never will have more than log n, because we always use this binary representation to sort of store, to denote how many trees we have. So then we're going to have more than log n, or log n minus 1, but log n number of trees. So now, okay, so far, let's take this, supposed to be like this. So, all right, so far, great. We can do this insertion of log n time. All right. I mean, we already had binary heaps, which also takes O of log n time to insert. So, okay, so why did we spend, an hour today talking about this, and maybe spend about 10 minutes last time going over binomial trees? Because, okay, We're doing this very complicated, convoluted structure just to do exactly what we've been already able to do, which is a logarithmic insertion. Well, here's the deal with binomial heaps. So we can amortize um, cost insertion. So here's the other sort of trick to this. Not every insertion takes O of log n. In fact, several insertions take, yes, roughly constant time, which I guess the word roughly is going to be a very loose definition right there. So the idea is that not every insertion is going to require us to have to insert and build everything into our tree, because for binomial trees, we're not going to insert to the back and then bubble it up. So for binary heaps, every time the worst case could happen, every single insertion, because you could have to bubble the element all the way up to the root every single time. But a binomial heap, we're not bubbling anything. We're just taking a B0 tree and merging it with our existing forest or existing binomial heap structure. So several insertions will be very fast. And we'll have that one bad case where after we do several insertions, we have that one case we have to do all that log n time together. But not every single time we're going to have to do this. I mean, we can kind of figure out how often this is going to happen. So as we add ones, there's going to be always that one case where it's going to add everything together after X number of merges. So that means that we can amortize it, that we're going to have to do this logarithmic work only sometimes, not always. So actually, in fact, if we amortize this cost, the overall sort of time will be actually constant. So I'll just not put that there. I was going to say that I'll say that the amortized cost for insertion is O of 1. So I can't really prove this, but I looked around in the book and I sort of researched this, and it is O of 1 is amortized cost. So remember what amortized analysis is. Remember, it's like we're not going to always do the worst case every single time. We're not going to always do the most work every single time. Because the worst case, if let's say we have a B3 tree and we're adding a B0, the worst case will be O of 1. It's not going to get worse than O of 1 because it just simply just merged a B0 tree into the B3, call it a day. So the thing is that just like, the amortized analysis I discussed last time, you're putting gas into your car. You could put $2 in every single day and go somewhere, or you can put $40 at one time. After 20 days, you have to refill your tank. So if you sort of average that whole thing out, it'll be $2 per day. Not going to be $40 every single day. You pay $40 at one time, but then afterwards, you don't have to keep paying every single time. So it's the same idea here. We have that really bad scenario where we have to do that merge, which will take logarithmic time, but that only happens sometimes, not always. So then we can average that out to be roughly, if you overall average out the complete cost, it's going to be constant, which is better than doing a regular binary insertion, binary heap insertion. So using sort of this binomial heap or Fibonacci heaps can be better than using a regular binary heap for Dijkstra's algorithm because, or for any type of algorithm that uses a priority queue because of this amortization. And of course, you can go into more detail and think, well, there are moments where the constant can be very bad, and I don't want to go into all this detail right now. But that's sort of the idea of why we do binomial heaps. That's the whole benefit of it. But the input size has to be big enough to really see any real difference. So, but of course, typically the input is going to be always relatively large. So that's sort of the idea. Now, of course, just like with a binary heap, if I wanted to update, let me go ahead and just sort of write this here. if you want to update element in the binary or binomial heap, binary or binomial heap, runtime is O of log n. I'm not going to really go over the steps for this, but just like, so for binary heap, if you want to update a certain element in your structures, you're going to have to maintain some pointers or some other structure so you know exactly where in the heap this element is going to currently reside in. You can update that and bubble it up from there. Well, for binomial heaps, same idea. If I want to update, I want to update this, let's say 7 to the value -1. You can update that and then sort of bubble it all the way up to the top of your tree if you wanted to. You could also bubble up just like you bubble up with binary heaps. So you never ever bubble down ever, because whenever you insert something, you go into this merge, not insert, and then we're never going to bubble down actually. So we'll go over deletions next time, but there's no bubbling down going on with binomial heaps, which is actually makes this process a little bit simpler. Or not so bad, because bubbling down would be a real pain if we had it for this type of structure. So the idea is that updating an element and then bubbling it up is also log event. So that part is not going to be hurt. So it's going to be the same runtime as binary heaps, but the insertion time is where we actually kind of gain. And deletion also can be beneficial, but typically deletion is not going to be so great. So we'll go over deletion into a binomial heap next week. So for now, I think we're almost out of time. So I think I'll go ahead and end class right here. So take care, you guys. Stay safe. Thanks for watching. Have an awesome weekend. And I'll see you guys on Tuesday.